Okay, 2015 AP Calculus AB free response questions. Let's begin with number 1. This is calculator active. It would be practically impossible without some sort of computational device. All right, the rate at which rainwater flows into a drain pipe is modeled by that function, cubic feet per hour, measured in hours from 0 to 8. You don't have to write this, but as I begin to think about what we're really going to do with this problem, I think it would be a really good idea if we just started doodling some of the things that we know or could come in handy. So here's what I know. We are putting water into a drain pipe, and it is going into a drain pipe at R of T cubic feet per hour. Okay, so that's just going to come in handy. And they gave me an interval here. That interval is really going to come in handy as well because it is going to correspond with the other function they're going to give me. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of T. Okay, so this is out. So in is this, and out is this one. And it's also for that same interval, and that's really convenient. For 0 to 8, of course, there are 30 cubic feet of water in the pipe at time t equals 0. I'm going to write it down. Maybe I need it right now, maybe I don't. A lot of times if we're struggling with what to do in a problem, you may just want to write down what you know and things might jump out at you, really. I've seen other people do the same strategy even when they were tackling a difficult problem that they didn't know, like really intelligent people that were struggling with difficult problems. Anyway, I digress. At t equals 0, there are 30 cubic feet of water. There we go. I'm just doodling some thoughts. So let's go ahead and start answering the question. How many cubic feet of rainwater flow into? Okay, when they're talking about this one right here, R of T, flow into the pipe during the 8-hour time interval from 0 to 8. Well, if I want to know how much flows in, if I want to know the quantity, then I can integrate the rate. And we've talked about this before. If I take the integral of a rate, I get the quantity. And I hope you realize that this is a rate, not because it's R, but because it's cubic feet per hour. This is a rate, also cubic feet per hour. So if I integrate that rate, I'll get the quantity. I want to know the rate at which it's going in. Part A is the easier of the 4 parts. So from 0 to 8, we will integrate R of T, dt, and we'll find out what it is. If you want to write the actual function down right here, that's fine. If you want to put R of T, that's fine. It's already been defined. So very quickly, I'll go through this process. It will come in handy for us if we will go ahead and type both of them in. So 20 sine t squared, oops, I'll put x, of course, t squared over 35. That's going to be R, that's y1. And d is going to be negative 0.04 t squared, whoa, t cubed. Let's fix that, not to the 23rd, there we go. Plus 0.4 t squared plus 0.96 t. Make sure I have everything right, and I believe that I do. And that's it. Okay, so let's just integrate from 0 to 8. So 0 to 8 of R of T, there we go. Now, I'm using X, of course, and so they did not tell me to use units, but it's a great idea, so let's do it anyway. It's a really good habit to have. So this was 76.570. I know it's a 0, but you put 3 decimal places, okay? 570, and I'm just going to put cubic feet. They didn't ask for it, but there you go. The people who grade this are going to be looking for 2 things on this part. And the first thing they're looking for is the integrand, and the second one they're looking for is the actual answer. So there are 2 things right here, integrand and answer. Okay, let's do part B. Is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. Okay, so when things are increasing or decreasing, then their derivative is positive or negative, right? Okay, we could think about it like that. We're thinking about it like that, but technically they gave us the derivative in a sense. They gave us a rate of change. So they say, is the amount of water in a pipe increasing or decreasing? They ask what happens at t equals 3. So here's all I really need to do. The water's going in at this rate, it's going out at this rate, and they've given me rates. if I take what's going in and subtract what's going out, then I will have the flow of water, the rate of change of the flow of the water in and out. It'll be a combination of the two. So what I'm really doing is, in some small sense, I'm kind of making up a new function. And here's my function. So the rate of flow of the water is just going to be like R of t minus d of t. And it makes sense. This is in, this is out, right? Well, I want to know what happens at t equals 3. So I'm taking that idea. That was just a little mathematical doodling. I'm going to actually do the work here. R of 3 minus d of 3. And I'm going to find out what this actually is. So then I grab a calculator. I'll set it here where that awkward shadow has probably been bugging you the whole time, right? And now you can't look away. There it is. So I'm not integrating, I'm not taking a derivative. They gave me a rate. They asked for something that involved a rate, so I'm using the actual function itself. So there we go, there's R of 3 minus D of 3, and I get negative 0.314. Negative 0.314. Okay, well, now what? Is it increasing or decreasing? My rate of change is negative. So because it is negative, I know it is decreasing. So let's read a problem again. Give a reason for your answer. Oh, I better do that. So the amount of water is decreasing at t equals 3 because R of 3 minus D of 3 is negative. Now, the answer key actually words that a little bit differently, and here's what they actually did. So this is all right, nothing's wrong about it, we're all good. However, they went a little bit further with this little statement right here, and they said R of 3 is less than D of 3, and this actually requires very little calculus. It's more like common sense. What's going in is less than what's going out, so the amount of water is decreasing. Okay, so remember, this is in, this is out. So at that moment, what's going in is less than what's going out because they added the D of 3 over. And it makes sense. You could really just kind of plug them in and compare them and see which one's overpowering the other one. So the way they graded this one was that you had to consider, let me show you the answer key. You had to consider R of 3 and D of 3. So we thought about that. That was on our paper. And then the answer and the reason. So the answer, which of course was the fact that it was decreasing, and here was our reason, and that was their reason, but it's the same idea, just manipulated the inequality a little bit differently. All right, so let's move on to part C. Pardon me. At what time from 0 to 8 is the amount of water in the pipe at a minimum? Okay, where do minimums occur? Where the derivative equals 0, okay? Justify your answer. Okay. This is about to get a little bit tricky. So I want to know when I have the least amount of water in the pipe from 0 to 8. Well, I can't just always necessarily... Here, let me show you what's going through my head right now. Okay, how much water is in this thing? How much water is in this drain pipe? Well, it depends on when you're talking about, okay? So I'm going to slide this up a little bit, then I'll zoom it out. You can see a little bit more of it, and the shadow goes away. There, lucky you. If I want to know how much water is in the pipe, I want to know the amount of water in the pipe, when is it a minimum? So if I want to know exactly when that takes place, well, let's just start kind of thinking through this logically. And let me take you through my thought process. If I want it to be a minimum, then I know maximums and minimums occur where the derivative equals 0, okay? So where the rate of change is equal to 0, and this is my rate of change, what goes in minus what goes out. And it also occurs at the endpoints of an interval. So I'm going to write that down. That would be a waste of your time to write that down at that exact moment when you're taking the test. You don't have to look at that and say, well, this happens at the moment where the endpoint and no, you don't have to do all that. But I'm just kind of writing down my thought process. So we will check the endpoints. And we also need to check where I would say the derivative, but I'm going to call it the rate equals 0. So we're going to check both of those. So that's kind of what's going on. This is not necessarily part of our answer. That's just reminding us of what we're about to do, okay? So let me slide this paper out of the way, slide this thing up. And at what time is the amount of water in the pipe at a minimum? Okay, well, the endpoints, that's going to be at 0 and at 8, right? Okay, so we have that. And we might have some other stuff inside here. So we have some time 0, time 8, and then we're going to have the amount of water. So I'm just going to write quantity of water. Well, let's just go ahead and go for the obvious. How much water do we have in the tank at time t equals 0? 30. There we go. How much do we have in the tank at 8? I don't know, but I'm just thinking ahead. And again, I'm taking you through my thought process. As I think about this, I need to consider that I would start at 30, just doodling over here, and I'm adding this much. Now, I can't use t here. I have to use something else because I'm using t up here. And then I'm subtracting this much from 0 to t. So at any given time, I had 30. I put this much in and I took this much out. Okay? So this is my quantity right here. This is my quantity function. So if I want to know how much there is at 8, I can use that function right there. So let's actually do that. We'll find out what happens at 8, and then we'll actually get to some of the other ideas. So 30 plus math, 9 from 0 to 8 of 1 dx minus math 9, 0 to 8 of y2 of dx. And that gives me 48.544. 48.544, and technically that would be cubic feet. So putting it back in context, I want to know when it's a minimum. Well, so far it's that. Well, I also need to know where the rate equals 0, and we have a couple ways of thinking about this. If I took the derivative of the quantity, I'd get the rate, and that would wipe this out, and that would give me r minus d. But I also kind of know that my rate is already that anyway, and I need this to be 0. So here's what I really need. I need r of t to equal d of t. So basically that came from me saying if this equals 0, then the rate at which it goes out is the same as the rate at which it goes in. I pointed at the wrong ones in that situation, but there you go. So I'm going to find out where they actually equal, and we'll do that graphically, and that's why we have a calculator for this. So y equals, I'm going to set my window to go from 0 to 8, and zoom 0, zoom fit, and that will tell me where these two functions equal. In other words, the rate in equals the rate out. And that occurs here at 0, and it occurs here wherever there is. So we will find out what that is. Let me zoom this back down, or slide the camera back down a little bit. There we go. And I want to find out where that is. So second and calc, we're going to find that point of intersection. Enter, enter, enter. 3.272. And that's the only one, other than 0, but we already had that. 3.272. Okay, so let's recap. I know I'm taking longer than the allotted 15 minutes by the time this whole thing is done. I know, but I'm explaining a lot. So, for this problem, for part C, they said, at what time do we have a minimum? Maximums and minimums occur at the endpoints of an interval and where the derivative equals 0. So where r of t minus d of t would equal 0. Just in case you need to write it, you could put this here. And that's where I got that. And that's where I got that. And that right now is my x value. I'm going to save it just in case I need it. So x stores to a. Whoops. I'm not going to write that down. I'm just going to use that, okay? So I have that exact value if I need it. So I'm going to find out how much water we had in the tank at that value. So let's go back up to our little function up here. And actually, I'm going to go back up to that right there. And all my 8s are going to become A's. I can't keep it as X. It would mess everything up. All right, well, 27.965. 27.965. Okay, so at what time is the amount of water in the pipe at a minimum? Justify your answer. The water is at a minimum at t equals 3.272. What is this measured in? Hours? Yes. Okay. Have we justified our answer? I believe through the process of our work, we have. In the process of all that we have done, yes, because I believe that we have, first of all, considered this. That's worth a point. Our answer is a point. And then the justification is a point. Let me show you what they put. The justification is 1 point, and their justification really did involve this chart. So notice I said quantity, and they said amount of water in the pipe, and so they had 0 and 8, and they also had that number, 3.272. Okay? So we have our justification, so that is justification, and that really came from this first idea that we had right here. All right, let's do part D. Again, I know I'm going over the 15 minutes. I apologize, but I am trying to explain very thoroughly the thought process. The pipe can hold 50 cubic feet of water before overflowing. Excuse me. For t greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. All right, here, let's realize what's going on. Originally, they restricted us between 0 and 8, and now they're saying, you know what, these functions are going to continue beyond 8. I'm just throwing that out there, okay? For t greater than 8, water continues to flow. Write, but do not solve, an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, well, here goes. When I did this one, I did it wrong. And I did it right, but I did it wrong. And I'm telling you that kind of as a cautionary tale to make sure you're reading the problem very carefully. The time w. My answer involved time t. I also had another mistake because I put t here and here. They told me to let the time be w. So here goes. I want there to be 50 cubic feet of water. That has to do with this function that I've already defined right here. So here's my equation. I want it to be 50. My quantity needs to be 50. I start with 30. Oh, can I subtract and make it 20? Yes, but they said not to solve it, and don't make it harder than it is. Plus, it starts at 0. It ends where? I don't know, but the time will be w. I'm going to stick with r of t dt. Now, you can't have the same variables here that you have here. That is mathematically awkward and wrong. Let's make sense of this just to make sure we understand it. The quantity is, well, 30, because I started at 30, plus what I've put in from 0 to w, minus what I took out from 0 to w. And that's all I had to do. Don't solve it, just write it. And the integral itself is 1 point, and the equation itself. So here's the whole thing. But if you have these integrals, then you have another point. And by the way, they did it differently, but we're not wrong. They put both of those integrals together. They did 0 to w and then r of t minus d of t. But it's the same idea if we're using the properties of integrals. And they did say involving one or more integrals, and we used more than one. So there we go.